Welcome. In this video, I'm going to explain a little bit more about the Wilcoxon signed rank distribution. It's not about how to obtain this distribution, or not so much. It's more about what it actually is. And note that there's also a Wilcoxon rank sum distribution, which is actually different. This distribution is showing how many different ways you can get a sum of ranks of a specific value, t usually defined. You can actually get if there are n unique ranks. So if you have ranks going from 1 to n. The distribution will then look something like this, for example, when n equals 5. And therefore, if we have our t value at 6, for example, we can then see from this distribution that there are 3 different ways to actually obtain a sum of those ranks of 6 in 3 different ways. Now, those 3 different ways would, of course, be if you have a rank 1 and 5, so 1 plus 5 equals 6. 2 and 4, so 2 plus 4 gives 6, and 1, 2, and 3 altogether also gives a sum of 6. Note, by the way, that the possible range is, of course, 0, which means that you don't have any ranks, and the largest one, in this case 15, would be the sum of 1 to n. So that means in our example 1 plus 2 plus 3 plus 4 plus 5, and that indeed equals that 15 that we see over here at the end of the distribution. The math notation for this would be something like this, or sometimes you might actually see it written differently because it can be shortened to simply doing n times n plus 1 divided by 2. So in our case, that would be 5 times 6 divided by 2, and that indeed equals also 2 by 2, and that also gives 15. Another notation you sometimes see is the binomial coefficient, or the combination formula, which is n plus 1 divided over 2. It's actually not over 2, it's just this notation, which means which has a special function. But in the end, that simply gives the same result as this one. We're usually not so much interested in the counts themselves, but actually use those counts to determine the probability. So for that, we need to divide it by the total of all the counts. And if you think about it, we actually have, if we only have one rank, then it can either be a 0, it can either be used or not. So that's a sum of 0 or 1. So we only have 2 options. If we have 2 ranks, then we can either have each of those ranks being used or not used. So that's 2 options for each. And then multiply the 2, and that means we then have 4 options. If we have 3 ranks, you can have each of them either selected or not. So we get 2 to the power of 3 equals 8 options. So in general, we can say that there are 2 to the power of n options. We can use this to determine the probabilities. So we can simply take the count that we saw with the previous one, and then divide that by the total number of possible distributions. So in this example, what we would do is we would take, for example, here for this one, we would take the 2 and then divide it by the total number of probabilities with an n equals 5. That would be 2 to the power of 5, which equals 32. So we would then divide that 2 by, we would divide this 2 by 32. And that gives you a distribution that looks exactly the same, but now, of course, the scale is actually showing the probabilities. Besides the regular probabilities, we're often also interested in the cumulative probabilities, which simply means to add all the previous ones. So using our same example as before, we now have the probabilities, and for the first one, the first column, there are no previous ones, so the cumulative probability is simply the same as that probability. So we just put the same one there. For the 1, it's actually therefore going to be 0 plus 1. So we add these two together. And then we do the same for 2. So we get 0, 1, or 2, and we add them all together. And for 3, we do the same thing again. We add them all together. Another way of, instead of adding each of them together, is to take the previous result, this one, and then simply add only the new one. We can keep on doing this for all of them, and then we would get something like this. Let me erase all these. This goes on for quite a while, so let's rescale that so you can see the whole thing, and perhaps even rescale it a little bit further, and then we have our cumulative probability distribution. So for example, to get a sum of ranks of 6 or less, we can simply look at that that's going to be about 0.4. This distribution is symmetrical, so that means that, for example, having a 6 or less would be the sum of all of these, the highlighted ones in red, would be the same as if you take from the center the same amount, the same as 9 or more. So all these yellow ones together should give you the same value as all the red ones together. If the sample size is large, this distribution will actually start to look like a normal distribution. The normal distribution is also symmetrical. It will form a bell shape as well, but is a continuous distribution. This one is discrete, meaning that there are no in-between values. We either have a sum of rank of 0, 1, 2, but never like 2.3 or something. This will only start to apply if therefore n equals is large, and large can be defined in different ways, and different authors have different opinions about that. So here are a few that I've came across that use actually different settings. I would say about more than 25 should be large enough, and then this whole distribution can be approximated by using the so-called normal distribution. The most complicated thing about creating this distribution is those counts. Once you have the counts, it's fairly easy to determine the probability, and once you have the probabilities, it's easy to come up with the cumulative probabilities. To determine those counts, different algorithms actually exist. You could, of course, just enumerate all the different options. There is a recursive formula. The advantage of this one is for a specific t-value, it can just calculate only that one. Downside is if n becomes larger, then this is fairly slow. The shift algorithm is faster if n is large, but it will actually calculate the entire distribution for a specific n, and then you actually just look at the value you're specifically interested in. Another option would be the split algorithm, which splits, as the name implies, all the calculations in two, and it uses some symbolic math for it. There's a Fourier method, and there's a network algorithm, and there's a Yale who actually optimized a few years ago. I think it was the shift algorithm. He combined some of the algorithms, and that's a different approach. Now, to do this, you could of course do it by hand. Sometimes people just simply look up tables, and another way is of course to use some software packages. SPSS, to my knowledge, does not have a separate function. If you would go for compute variable, I couldn't find something that can calculate this distribution, but it is capable of using it. So it has it somewhere under the hood, somewhere in its engine, if a test requires it. With Excel, there's no built-in function that you can use directly. I've made it available in my own add-in. So if you're interested in that, it will be available on my website. Python, also to my knowledge, has no function that can actually do this directly, and I haven't found any other libraries yet that can actually do this. So I made my own. It's available in my stickpad library. R does have a function in the stats library that comes with R usually. P sign rank is then for the cumulative density function, so that returns the cumulative probabilities. And D sign rank for the probability mass function, so that gives just the probability for that specific value. I'm not sure which technique it's actually using. There's not a lot of documentation about how these functions actually work, what they're using. I also made my own version of this in my stickpad R library. So if you're interested in one of these libraries, check out my website. I also explain there how you can do the manual calculations with some of the algorithms, and also how you could use tables in case you're still using those. All right, and that's a quick summary of how the Wilcoxon assigned rank distribution actually works, what it is. I hope this was helpful, and thank you for watching.